So what we'll be doing today is, in this session, is we will be looking at functions, programming with functions, functionals, why you want to do it, how to do it well, and the like. So for this, we will actually have actual programming. Yesterday I gave you some little mental challenges. Today I want to actually code up. So set up your RStudios, and I think it's more efficient if you pair up. If you feel like pairing up, pair up. What that means is sit next together, introduce yourself to your neighbor, and work in pair or triplets, whatever, quatuors. I think that's as much as we can do here. All right. Then I've created this shared document. Some of you are on it already. Let me make this bigger. So this is the URL. So this will be a way for you to communicate with me code, right? So you will code up, you can paste it in this window, I'll get it, and we can discuss, right? So we'll see how well that works. Okay? So,
you guys did Spring for a Slack?
Sorry?
You guys did Spring for a Slack?
Oh, you're cheap. And this works without any registration, right? Click on it, you're there. But we're cheap. So, good. Any questions before we start? We're all good? Yeah? All right. Yeah, don't edit the code, that part yet, because, yeah, well, I mean, yeah, don't. All right, so the first part, so there will be two parts of the lecture, and the first part will be talking in general about functions. So yesterday, in the intro to R, I presented some of the main points that you have to know, and we will go in a little bit more depth. But before we go and look at how to write code, I wanted to give you one example of, here's a piece of code. Let's see, can I make this bigger? So here's a piece of code. What does it do? Probably nothing very meaningful, but this is the kind of code you will see crop up. People. It starts nice, and then people start to tinker with it, fix something here, fix something there, and before you know it, yeah, this is the kind of code people actually write. And so now, if you look at it, well, what does it do? It takes as input a matrix, and in here we're just, I'm just creating a random matrix that's not important, and a result, which is also an empty vector, and then it populates the result with values computed from the matrix. The matrix has three rows, and it seems like it's doing something on each row if you look at the indices here. So there's like, yeah, if you had to guess, it's probably doing some computation, taking the different columns, doing some kind of extremely meaningful math to them, and then returning a vector of 3 values. That's code. Okay? So, is this good code? Would anybody defend this piece of code, saying this is the code I would like to show to my Google interview? maybe it does the job, maybe it's right, you know, but it sure isn't easy to read. And if there's one thing that you have to remember when you're coding, is code is read much more than it's written. Right? People read code a lot, write it only once, modulo the bugs. Right? Who reads the code? Well, yourself, then the person you're trying to convince that this is correct, then whichever are your users and so on. So, and then, you know, if the code actually does something useful, then there'll be maintainers. So there's the whole generation of people who will read code, only one person who writes it. So when you know this, you have to optimize for readability. And the point of functions is that they can provide us with the tools to build abstractions. So this code is doing a whole lot of things, but it's really difficult to figure out, looking at this code, what those things are. So you need to abstract those and give a sort of higher level view to the user and allow users also to decompose. Like they should be able to understand the code bit by bit. My claim is, if you want to understand what this code does, you have to read every single line. Right? Why? Well, because here it's doing things on R1, R2, R3, then R2 again, then R3, R2, R1. It's like completely jumbled, intermingled. It is a mess. All right. So, as a first challenge, you can take this code from the buffer, I shared it, and see what could you do to clean it up. Anything you do to improve it will win, a lot of gratitude from me. I will be very grateful if you can make this code better. So, 5 minutes. Let's give us that. 5 minutes. Look at this code. What can we do to make it better? And the interesting thing is, what is your thought process? How do you approach this? And then we'll compare maybe 1 or 2 solutions. Right? So the second. So for those who just came, we have a URL here for a shared code buffer. And we're asking everybody to take this piece of code, paste it in their favorite editor, and try to make it better. And we'll argue what better means. And it's okay to speak between yourselves. That's fine. So I think it's actually a good thing. I don't mind the buzz.
Should we preserve, I guess we should try and preserve whatever the current output is.
Right, so what should we preserve is a good question, right? So I think we can agree that it should do at least the same thing on the same input. That's that's first level of correctness. And then you have to sort of think, well, what if we change this input? What are other inputs where it would be, what can we reasonably expect this code to do on other inputs? And the more general the code, typically the better, because you can use it in more contexts, right? Hint, this is a section about functions. But you don't have to do that. There are many things you could do other than that. around, and if you have questions, just. So if you have some solutions or starting of a solution, paste them into the window, and we'll start looking at them. So I'll take this solution. So anybody else has a solution to share? I think sorry? Working on it, all right. Oops, maybe I did something wrong here. So one more minute and then I time you out. Not that I want to stress you, but we do have things on the agenda. Right. All right. Oh, what's the solution here? All right. So, shall we look at solutions? Yeah? Shall we? All right. So the first solution that was proposed is one where we take the existing code and we turn it into an abstraction that takes as input the data, the number of rows and number of columns, and otherwise does exactly as before, right? So this function takes y, n row, n col, and then calls matrix, does all the computation, and then returns R, right? So this is clearly correct. It does exactly as before, but I think we can do more, and certainly a starting point. So let's start from this one and work on improving it, and maybe we can reuse some of the bits from other solutions. So what were we doing here? So here we have a function f2 that decomposes the mathematical operations, right? It says, well, I take y, and here we assume y is one row of my data frame or matrix, and we operate on the three positions of y, 1, 2, 3. We build temporary results because we notice that we're always adding these three, and we're always performing the same operation. So here, what we're doing is we're taking and extracting that commonality. So let's combine both of these solutions, see whether that gives us something better. So I could say, so if I wanted to combine this, what I would have to do is, on this line, I would have to call f2 with as argument this y, which is the first row of x. So I would say x1 on comma, and then I can get rid of all this line, right? So that's already a little bit better. Do you agree that this makes sense? And the same way I can get rid of this bit of computation by calling f2 x of 2 comma, and in the same way I can get rid of this bit of computation by calling f2 x. Okay, so that's made my code a little bit better. What else can we do to make it nicer? So let's think about this bit of code. It looks like the programmer, when they wrote this, suddenly had encountered an NA and started to worry. They freaked. What did they do? They said, well, if this position that I'm going to read is NA, then I want the whole thing to be NA. But in R, if that position is NA, then adding it, multiplying it will cause an NA. So this is a whole bit of redundant code that is not needed at all. Because if 2, 3 is NA, you will get an NA. I can prove it to you by, let's see if this whole thing compiles first. Not quite, but close. So let me prove it to you by calling f2 with a vector that contains 1, 2, and NA. So my claim is this will result in an NA, and it does. So that code over there was just programmers not understanding the language and being super cautious. So we can get rid of that bit. Don't do us no good. Okay, so we made some progress. So code should be regular as much as possible. So if you look at this, you know, the statements seem jumbled. So let's just reorder them a little bit so they're more logically correlated. So things that operate on the third row should be together. Things that operate on the second row should be together. Let's see what that gives us. R2, R1, All right. So, okay. So that looks a little bit nicer. Then we can, oh, I think I messed up something. Oh, this is not nicer. This is horrible. That is nicer. And up. And you should correct me when I'm doing obvious nonsense. Oh, this looks like a bug. Where did I get two R2s as integers? I don't know. So this is called cut and paste errors. So you're moving around code, cutting and paste it, and you make errors. Okay, so this is looking. Which one? This one? That should be X3. Yeah, that's my mistake. I was introducing these indices. I messed up. So, okay. What else can we do? So, I think we can simplify this a little bit further. Well, we'll get to it. I think this is maybe a little bit too advanced. But what if we had a function f3 that does the addition, the squaring, and the two integering? So let's say we have f3 that does function. It takes a value v. It takes something to multiply it by. And, or no, so we are going to add it, and it does as dot integer of v plus a times v plus a. Is that semantically identical? Let me just do it carefully. So x is v plus a. And then we are going to square that x times x, and we return. So now we should be able to replace this by a quote of f3 of f2 plus 10, and we can get rid of this. We can replace this by a call to f3 or f3 of f2, and this was 100, and then f3 of f2, 1000. Okay, so now this is starting to look a little bit better, right? You can see the pattern clearly. The function fits in the screen. It's okay. Probably, maybe we could combine f2 and f3. Nah, whatever. Not necessary. So, okay, so do we like this? Is this a better solution? Yes? No? It's still, sorry? Still difficult to read. Okay, so what else can we do? We notice that we're doing something that is very regular here, right? We're accessing a row of each of these. We're adding a value. So there ought to be a better way to express this. I agree. 10 to the power of some number between 1 and 3, yeah, but that doesn't help because we still have to pass the number, right? So it's, well, let's leave it for now. We'll revisit. Another thing I wanted to bring up, names. Names are really important, right? So here we have empty function, f3 and f2. They're not meaningful at all. right? So what you want to do when you write code you care about is give names that give you a feeling, what is this doing? Because the names will help you read the code. If the name says we're squaring or we're doing something that is domain specifically meaningful, then you can read the code without having to go figure out what the function does. So names are super important. There's a lot to be said about which names to pick. I'll just say this one. Pick short names for things, for identifiers that are local to a scope. Pick long names for functions that are used throughout your program. Essentially, the wider the distance between the use of names and their definition, the longer the name should be, because you want to remember what it does. If you can see everything in a window, then a name like R and X is just fine. Okay? All right, so back to the plot. So the argument here is code has this ability to grow and become messy. We can structure it using functions. And there's a bunch of laws that, you know, software engineering people will tell you about. The first one I mentioned, code is read and not written, so optimize for reads. Avoid repetition. If you see two things that are doing the same thing, turn them into a function. And that's what we did, right? They were like the same operations, and we extracted the commonality, put it into a function. If you don't test your code, consider it wrong. You know, any code that you're not running daily is most likely wrong. So there was a friend of mine wrote this tool that would automatically delete any line of code that was not tested. Aggressive, but it had the right spirit. Did I mention that we should not repeat ourselves? So yeah, don't repeat yourself. Every piece of knowledge must have a single, unambiguous, authoritative representation within a system. So don't repeat functions, don't repeat the same method, just, you know, extract them, put them in one common place, keep them, centralize them. All right? Okay. So this was really about motivation. Let me give you another example, and this one maybe we'll do together. I'll be typing and you'll tell me what to do about it. So here's a piece of code. Here's a piece of code. So what does this code do? It creates a data frame that's built by calling the replicate, which calls sample, and the sample generates values between 1 and 10, and also sometimes minus 99. We do that 6 times to get 6 rows, and this will give us a data frame of 6 rows. Yes? So I can prove that this is what it does by running it. And now I can show you the result. It is a data frame with values that are between 1 and 10, with the exception of sometimes 99. So by default, the data frame has these auto-generated column names, but they're nasty, so let's just use attributes to give them more pleasant values. And let's print that data frame again. So now the column names are A, B, C, D, F, right? So name, DF is a data frame. Names is an attribute. So this is a way to set an attribute. Yesterday we talked about attributes. And we set it to the values of the 6 first letters. And we get A, B, C, D, F, right? No magic? Okay. So we have our data frame. And now, well, now what we're going to do is use the powerful subsetting features of R to get rid of the minus 99s and we're going to replace them by NAs. So this is a typical data cleaning task, right? You get data, the missing values were coded in the database by -99. You want to have clean data that uses NAs in R. So what you do is you're going to say, well, take the first column, column A, and this is a predicate, right? So this evaluates to a Boolean vectors, trues and false. For all values in that column that have value 99, replace it with NA.
You know C is 98, not 99?
Yes, I know, we did it on purpose because we're silly, right? Typos. So this is indeed just a typo, and you know, if you don't catch it, you don't catch it, and then you're not replacing the proper values. Yes, this is again, so this thing about no repetition, this is a repetition. I'm repeating the encoding of NA. I should not do that. I should have only one place where I say that my NA is -99, and that's it. Repetition is, each time you repeat yourself, there's a chance of making a mistake. So, just to bring back some of the things we showed yesterday, if I just print this expression, DFA equals -99, what do I get? I get a vector of Boolean values, and this is the positions in that column in the data frame where a 99 occurs. So, and to convince ourselves this is the case, let's just print df of A, and you see the first value is indeed -99. All right. So now, if I run this line, and now I print the same column, you see the NA has replaced the -99. We have achieved what we wanted. So we can do that for the whole data frame, and we will. And then we can print the whole data frame, and it will have, oh, there is still this -99 that comes from this guy that I should fix, really. And run again. What did I do wrong? What did I do wrong? Oh, F and G, right. That's another one that's fun. Yeah, that will happen. So this was obviously designed to show that programmers are human and all that. But, okay. So what can we do better? Thoughts, suggestions?
You can just check the data frame for where your -99 occurs and assign that index to negative to NA.
Yeah, so you could do that, and that does the job, but it's I think what you mean is, what is it?
DF bracket, DF equals -99.
DF equal, yeah, that's the one. Yeah, that's not the answer I'm looking for, because that's too easy. But it is a perfectly fine answer, right?
I guess the more explicit answer would be you would want to store -99 as some sort of variable.
So what I wanted to get to is to say, well, we can do this in steps using functions. Right? And the first step would be to turn this thing into an abstraction. I have a 99 eraser function that erases 99s. And then I can hide this bit. So I can do that, right? Let's do that. So, so let's say no 99s is my function, which takes what? It takes, what does it take? It takes a column of a data frame. So let's call it X. I don't have a good name for it. And it says if X is equal to -99, store NA into it. right? Okay, and let's see if I can. So I'll run this the beginning again to get a matrix that has a data frame that has 99s, and I'll call this with one column, and that didn't do anything because I didn't return the column, so I need to return the column, and that column didn't have an A's. That's odd. Oh, it's random, so I don't know. Let's see. What? So let's do B. B definitely has 99s. Ah, come on. Right. When I did B, it replaced those 99. So this is good. This is good, but it is not quite what I want. I would like a function that works for any value of missing that I choose. So let me add an extra argument. So let's call it my NA val. And what we're going to test is my NA val, x is equal my NA val, and we can give it as default value minus 99. So if you don't say anything, it's minus 99. But if you want to override it because you have another one, that'll work too. Okay? So now we have this bit, but that's not quite right for what we're doing. We need to still assign it back into the data frame. So this would be like so. And we have NAs in there. So my point is, we can create an abstraction, and then when you call it, this looks better than that, right? We've sort of hidden some of the gunk. The other solution you said is even better, but this is showing a different point. So we can sort of push things into functions. And so let's see, what else did I want to say about functions? So a lot of this we said yesterday. Yeah. So yesterday I was showing you code like this that I couldn't get to work because I had forgotten one trick. So I was showing you code where I had stored a function into a data structure, and I couldn't get this to work. So now I know. I Googled it. So you say list of no NN, and this creates a data structure that you can then access, and you can say x1, and that gives you the no NN function. So forget who asked me how to do it yesterday. That the way to do it is you have to put all of your functions in a list, and you can have a bunch of those. All right. So what else did we do yesterday? Well, I'll let you do this one because it's easy. So here's a specification. So let me just do this. So here's the challenge. You have to write a function f and a variable and variable x such that when you call f with no arguments, it returns 0. When you call it with these two, it returns -1. When you call it with these two, it returns. It returns 1. Yeah, it returns it returns 1. For when you call this with these two, it returns 1 as well. And when you call it like this, it returns minus 1. So what would be a function that does very little, that satisfies this? So you have to define, you have to write f is a function of some argument that returns something. X is, something such that these things hold. So let me create a test case out of this so you can test it. Okay, so I will. All right, so you can run this test. I'll paste it in the shared buffer if you feel like it. And this, if you give it the right f and the right x, it should just work. So I'll try to define that myself. Oh, what is the expected result? Yes, the expected result is so I can't do that. So I have one solution that doesn't work. So what would it be if I say 1? What is the expected result? Expected result is Which one?
If there are certain values, then return.
These are the values. So it's I put it in here.
So those are the one things that have to return.
Yeah.
If it's something, then return those values.
Oh, sorry. So it's in the same order. So it should, if you run this test, you should return a vector. This is the vector that it returns, and it should be 0, -1, 1, 1, -1. So, I'll pause this. I'll give you one hint, and then we'll come back to it a little bit later. The hint is that you have to play with default values and the ... And there's only so many combinations, but it's if you can get it, I'll be very happy. So I'll leave this with you for now, and let's just go back to the rest of this. Do it at the break. So, right. So one thing that we mentioned briefly yesterday, but that really is important to understand when you're designing functions, is this business about the fact that arguments that are passed into functions are not passed by reference. So I'll explain this better. In languages that you may have used, if you've used C, if you've used Java, if you've used Python, when you call a function, you pass a value by reference. That is the technical term. And what that means is the function can change that value, and you will see those changes. You will observe those changes. So you pass in a big vector, the function updates it, then you see those changes. And in R, it's just not the case. And why did they design it like that? They designed it because they wanted to have something that is closer to mathematical reasoning, right? In mathematical reasoning, I don't have side effects. If I have f of x twice, x hasn't changed. I can write, if I have f of x plus f of x, I can write 2 times f of x, and that's true. Whereas in a programming language, that could be, in like Java, that doesn't necessarily hold. So they wanted to have that property, which is sometimes called referential transparency. And the way they do it, and I sort of mentioned that yesterday, is that essentially you can think about it as if every time I call a function, I copy all of my arguments and give them that copy to the function. So if the function changes them, it doesn't affect me, right? So what does that mean in practice? If I have a big table, 10 megabytes, 100 megabytes, big data frame, pass it to a function, that function changes it, it has to send back a result. So it means two things. That table will be copied when I pass it, and I have to get it back from the function if I want to use it further. So that's a change in the way you program from Java, C++, and the like. It can be really a problem for performance, because if you have large data structures that keep getting copied, that is going to take time and memory space. So most of the errors that we've fixed when we help people improve their R code have been, the speed-related ones were because they were copying too much. They had data that was passed to a function or copied, and that caused them a lot of grief. So this is an approximation. The reality is you only copy when you actually do the update. So R is trying to be smart and saying, well, if I give you this 10 megabyte data and all you do is look at it, I don't need to copy it. It's when you try to modify it that I will create a private copy for the function. So this is the copy on write behavior. So, and that means it's sometimes tricky to understand the performance of our code, because if you pass it to a function and for once, and that time the function doesn't modify the data, the function will run fast. The next time you modify the data, the function will run slow. So I'll show you an example how that can manifest itself. So let's say I create myself a big vector, 1 to, I don't know, 10 million, yeah, 10 million entries, something like that. So that's a biggish vector. And let's say I pass it to a function. So I create a function, f function, that takes x and returns, you know, some value out of that x. And let's say I will do that a number of times. I1 in 100 f of x. So let's see. What is the syntax here for I? Okay. Let me just write it. That should be enough. Check. Do a bunch of times, and so if I run this, so notice this returns immediately. Now let's do something else where I update the vector to value 12. That's still fairly fast, so we can just up the size, and we'll eventually. Now you can see the machine is thinking. So I run this, and you can see it takes a little bit of time for it to answer. Now I change this to be just a function that reads the data, and it's still immediate. So reading the data is immediate. If I have to make copies, it gets to become longer. If I do this if I do this 10 times bigger, you can see our wait times are starting to increase. So notice, we're waiting still. What are we doing? The only thing we're doing is we're taking that big matrix and we're changing one value of it. We're still waiting, right? So the point is, if you don't know what R is doing, the difference between that function that did modify the table and the one that doesn't is really small. Look, it's still thinking, right? It's probably going to come back sometime, but So we need to understand what is happening, and sometimes that means functions are not the right answer. You may remove some functions to improve speed. That may happen. Only do it if you have a speed problem. But if you have a speed problem, well, you have to look, well, am I doing a copy somewhere? Well, this is really, really, really dead. Can I kill it? Yeah. Right? So, that wasn't so hard to get to a point where R completely freaked, right? Okay. So, why did the R designers do it? Well, because the alternative is that you would get code that is easier to write wrongly. You would get code that has more bugs. So they decided to do this thing with the copies to help programmers to write code that is correct. It has a price, and the price is sometimes, your computation will just languish. All right. So we were talking about names of functions. So sometimes you may want to use very short names such as plus, right? Sometimes it just may be the right thing. For instance, maybe the right thing to add strings. If you have to do a lot of string operations, maybe what you would like to do is say hi plus bye. And sadly, R will say no, because our plus operation is only defined on numeric. Thank you very much. So what can you do if this is what you want to do? Well, the obvious thing is you're going to redefine plus and say that now plus is a function that takes A and B and concatenates, pastes A to B, and now hi and bye works just fine, and all of your arithmetics is going to work just fine too, right? Right? These are the expected results for addition. No, maybe not. So sometimes redefining plus could be the right thing, but it's very rarely the case. What you want is you want to be able to define your own version of plus that doesn't collide with the built-in arithmetic operator. And R lets you do that. It's just a little bit more syntactically heavy. So what you can do is you can define this percent plus. So you notice I'm putting quotes around this, and I use percent plus as my operator. I define it as before. And now if I want to add strings, I just use percent plus, and I add strings. Well, that's pretty cool. So you can do that for any symbol. The percent is recognized by the R parser and the language, so you can use it in any symbol, and you don't need to put parentheses. It can be inline like any operator. So you can extend the language this way. And it's, for instance, if you've seen the tidyverse, they have this pipe operator, right? This is how they do it. Okay. All right. Let's see. All right. So there's one other bit of R that is kind of amusing, and it is the way function arguments are evaluated. So let me explain this to you slowly. So let's start with print. Print is a function that prints its argument. So if I say print of 1, I get 1. Okay, that's easy. Now let me define a function that doesn't do much. It is a function f that takes 2 arguments and returns 0. And what is this invisible thing? Invisible is a weird thing in R that can be that is used to say that the console should not print that value back. So I'll show you what I mean. So let me define f. If I call f with 2 values, it returns nothing. Now if I change f to not be invisible but just to have a 0 in it, what would happen? Well, it would print 0. So invisible is just a way to tell the console, this value that you're returning here, don't mind it. It's not really important. You still return the value, I can catch the result of the call. I can say f is x is the result, and if I print x, x is here, it's indeed 0, but when I call that function, the interpreter will not print it, the console will not print it. Okay. So all of this was built up. So here's the interesting mind game. If I have a function f, this one, and I give it 2 arguments, which are print1, print2, what will happen? So print prints the number, okay? So what should happen? Will I print 2, then 1, 1, then 2, sometimes 1, sometimes 2? What should happen? Well, it's lucky, we can test it. If I run this, nothing happens. We're silent. That is odd. So, often we have a mental model of how a language works, and we have some idea of things that should be equivalent. So, in most languages, line 205 and 206 should be equivalent. What's the difference of between those 2 lines is this one I evaluate print, store it into a temp, evaluate print2, store it into another temporary variable, and then call the function with those 2 temporary variables. Do you agree that these are doing the same thing? Does that intuitively make sense? No, it doesn't? So, is it the print that is throwing you off? So let's say I remove the print and see if that would make more sense. Say this. Come on. So, can we agree that obviously calling f1 with 1, 2 or calling it with temp and temp2 should be the same? That makes sense? I mean, if we don't agree on that, then, you know, we're back into magic thinking, right? Because we have no clue what's going on. So let's claim we do. So why would it be different if I add prints around these? I mean, that's, you know, that's kind of innocuous looking. I'm just, you know, on the way printing the values. Can't hurt. So, mental model. If I execute this, what happens? Nothing. If I execute this, what happens? I print 1 and I print 2, and then nothing. So what's going on? What is going on? All right, I'll give you another one that is fun. Still same space. I'll do A plus B. Let's see, I'm not sure this will work. It may or may not. Let me try. So I change the definition of f, and I run the same thing again. What will happen? And now I'm printing 1 and 2 suddenly. Right? And so I said A plus B, and then throw away the result, return 0. Yes, when I do that, I print 1 and 2. So mental model, what is the mental model we should have? It's a complicated one. What is going on in R is that unlike most programming languages, when I call a function, I don't evaluate the arguments to pass them to the function. I leave the arguments as little boxes. They call them promises. And say, if the function needs those arguments, we'll open the box and see what's inside. When we open the box and see what's inside, we print it. Schrödinger cat, right? It's not there, you open it, oh, there was a cat. So, same thing. And why is this different? Well, because when we do this assignment, we're forcing the promise. We're forcing the evaluation. In order to store something in temp, we have to know what is inside that box. So, why is this important? Well, it's important because now the order in which things happen can change very, very quickly. Say I have this definition and I just change it to be B plus A. A plus B, B plus A, same thing, right? Now I call F print, and now I'm printing 2 and then 1. Because I'm touching the second box first and then the first box. Okay? So a lot of the magic in R comes from this. Because sometimes you will see things happen in a weird order. Sometimes you will see things not happen. And also, R can use the fact that these arguments are evaluated in a delayed fashion to its advantage. So let me show you how that happens. By the way, what time? What's the time? 15? Okay. So let me show you what we can do that is interesting. So I can, for instance, I can take one of these arguments, substitute, and use the substitute function to get at the code of that argument. So let me explain that in a little bit. Well, no, let me just run it and you'll see. So now what happened? Rather than printing 2, what happened is I printed the expression, the code that I passed in. I can change that code. So I can say, I can turn it into a string, for instance. Will that do? Right. So now I have a string, and I can, if it's a string, I can maybe add stuff to it, paste. I don't know, I can add +1. And let's see what happens here. Come on. And now I have print 2 + 1. And I can even decide to evaluate that code after I've changed the code of the argument. And let's see if that works. Eval. Yeah, I have a typo, but I'll show you a little bit, another piece that does this right. What is it? Eval parse. Oh, text. That was the thing I was missing. And that doesn't do anything because we're passing in. Oh yeah, and then we have to. Yeah. Okay. So sorry, I got myself confused. So the point, I won't try to fix it right now. The point is, the arguments that I get here are expressions. I can take their code, I can turn it into a string, I can change their code, and then I can evaluate it again. I'll show you an example that I actually have working. And why is this interesting? Because this is the way R implements a lot of the language extensions. All the little languages, formulas, they're implemented by turning the arguments into expressions that you then manipulate. So, for instance, you'll get that in the slides, but here is a small function that does timing in a reproducible way. So if you want to time an expression, this function tm takes an expression like 1 plus 1, it gets the code out, so substitute deparse, then it creates a new piece of code where it puts a timer, a call to system.time, around a loop when I run that expression n times, and it calls eval, and then once it has run for enough time, it reports the time it took. So you pass it 1 plus 1, and it will eval and tell you how long 1 plus 1 took to execute. And it said 1 plus 1 takes 0.0004 milliseconds, not that long. Okay, so this delayed execution is a key way to get R to run fast, to be extensible, sorry. What else do I have time to go? All right, so we'll switch now to the next bit, which is, where is that? The next bit, which is about functionals. So, all right. So back to this example we were looking at, and now we're going to do it right. So remember, we had our data frame, which had these columns with 99s, and we had a fix missing function or no NA. Here, it's done pretty much the same we had before. And then we had code that was going through every column and calling fix missing on it. So we can do better. We can do better by observing that we're doing the same thing on every column of this data frame. So there's got to be a way to abstract that. And indeed there is. The lapply function is going to do exactly that. So what does lapply do? It takes a list, and for every element of the list, it applies a function. So what is the function? What is our list? Well, our data frame is the list. It's a list of columns. What is our function? Fix missing. What we want to do is, for every column of our data frame, apply the fix missing on that column. Easy, easy. So we could write this as a loop. If we write this as a loop, we say for I in this sequence between 1 and the length of our data frame, apply the function f to the ith column and store that in the output's ith column. Right? That's one way to do it, but it's kind of wordy. lapply is a much nicer way to say the same thing. We say, hey, this data frame df, apply the fix missing to every column, and then give me back a new data frame. So what's interesting about this is we're using a function as an argument to another function. So this is lapply is called functional because it takes function and as arguments, and it's going to apply it to every one of those. And what you can do also is sort of you can say, for instance, no, I only want to apply to the first 5 columns, and that works completely fine. Selects the first 5 column, you replace the first 5 columns. So this is very powerful and widely used. Let's see. So what is lapply? If I had to code it and I didn't care about performance, it would look like this. Lapply is a function that takes x, which is a list, takes f, which is some other function, and first it creates a result vector, another list, and then for every column, say in the function, we apply f to that column, and the result column is stored in I of the output, and the output is returned. Okay? Does that make sense? Indeed, this notion of passing functions around is really powerful and maybe sometimes confusing. So, does this make sense? Let's get some examples. So let me create a list. So L is a list. Oh, that's too big. L is a list of 20 vectors. Each vector is obtained is a set of random values. Okay. So that's a list. So now let's take that list and oops. So what we could do is operate over the list, and for instance, say we want to know the length of every one of the vectors. So if we wanted to know the length of every one of the vectors, we would have to do the following thing. The first thing we do is we create an output, a result vector, out, and out starts empty. There's nothing in it. All we give it is we say it has the same length as L. And then we say for I, so what is sec along? Sec along is is all the indices in the vector. So it's the length of that list from 1 to 20. So for I in sec along, call length on each of them. So let's say I want to do length of L1. So that's 1. That's 2. And so on, right? So we do that, and oh, sorry. Copy, paste it here, puff. And we say out. Out is still a list, so we unlist it into a vector, and we have our result. So in our randomly generated 20 vectors, these were their lengths. So if we were to use lapply for that, what we would do is what we would do is simply this. We would say lapply my list, the length function, and then unlist everything into a vector. Same result. Okay? So clearly this is very, once you know how to read this, when you understand that lapply will walk through that list, apply length to every element, and then give you a list of results, this is much more readable. So, but you can do more interesting things with these functions. So you can apply them to data frame, to vectors, to matrices. You can use anonymous functions in there. So here's an interesting example. So you have this empty car data set. So empty cars is telling you something about cars, which I would not understand, but I assume is true. And I know they have a number of wheels, and I think there's a number of wheels. No, they don't. I don't know. They're complicated. But we can apply the thing that we can do, for instance, is, hey, I want to know what is the data type of each column. Well, there's this class function in R, which I can apply to the empty car data frame, and it will list me the mile per gallon is a numeric, and so on. They're all numerics. So good. So they're all numbers. So let's say I want to divide all of them by a constant. So I can do that by, again, writing lapply. Here I don't have a function that's already written, so I can write my own. I can say, well, hey, empty cars, apply this function. And what does the function do? It says for each value, for each column in the data frame, divide it by the mean of that column. Normalize it. So now, if I type empty cars again, well, the values are all between, all between what? One, well, I don't know. It has, yes, in the same range. So the point here is we have this, we have applied this anonymous function that I just defined here, and what it did is it used the column and it computed a mean and replaced every column in the data frame. So that is really powerful. So you can do the same thing with vectors. So this was with lists, but there are functions sapply and vapply for vectors. And they work in similar ways. And then you have another, how much? I'm done. So then you have another bunch of functions that you can read up on from the nodes, and these are map, reduce, and filter, and they work on multiple data structures. So if you need to traverse multiple lists or vectors, so map will do that. Reduce will compact all the results into a single value, and filter will throw away in different way or find values of interest. So that's it. So you'll find the notes on the GitHub, so the parts that I didn't get to are there. Thank you.